Hello class. So today we are going to be commencing our lecture on CHM 312, Physical and Structural Chemistry 2. And we are going to be considering dipole moments today, dipole moments under the molecular structure topic. We are going to consider both dipole moments and magnetic moments under molecular structure. But for this module, we are going to be looking at dipole moments. Now, what is dipole moment? Dipole moment occurs when there is a separation of charge. Before we can say there's a dipole moment, we must have what we call a separation of charge. Another thing is they occur between two ions in an ionic bond or between atoms in a covalent bond. Dipole moment arises from electronegativity difference. I want to quickly cast your mind back to what you have been taught before about molecular structures and bonding. You have heard of the ionic bond before. Ionic bond is a bond formed between a metal and a non-metal. For instance, for we to have what we call an ionic bond, that means we must be having a bond between a metal, for instance, a bond between hydrogen. Hydrogen is a metal, and then chlorine, which is in group 7, which is a non-metal. When we have a bond between the two of them, the bond that will be found here is a dipole, is a ionic bond. Ionic bond is formed between metals and non-metals. Whenever we have such a bond, we will see there will be what we call electronegativity difference. Electronegativity difference in the sense that the subtraction of the electronegativity of the two atoms or three atoms that make up that particular compound between each of the bonds, you will see that by the time you subtract the electronegativity, it will be greater than 0. You will not get an electronegativity of 0 as the difference. But in some cases, when we have a covalent bond, since a covalent bond is formed between two non-metals, it means that not all covalent bonds will have electronegativity greater than 0. What do I mean by this? If I have a bond between carbon and oxygen, which is these are carbon monoxide, this bond will have a electronegativity greater than 0. The reason being that the electronegativity of carbon and oxygen cannot be the same because they are two different atoms. According to the general trend, electronegativity usually increase across the period and decrease down the group of the periodic table. So it means that because oxygen comes after carbon across the period, it means oxygen will have a higher electronegativity. Let me just put, for instance, that the electronegativity of oxygen is 3. And then let's say the electronegativity of carbon is 1.5, or let's approximate it and let's just say 2, for instance. So it means the electronegativity that we'll have in carbon monoxide in that case would be 3 minus 2, which is 1. So it means that electronegativity difference is going to be 1 instead of electronegativity difference of 0. That means that electronegativity difference will not be 0. That's just what I'm trying to point out here. But if we look at it in another sense, this oxygen gas, which is O2, oxygen bonded with oxygen is oxygen gas. Both of them are having a bond of a covalent bonding between them because they are formed by two non-metals. But in the case of oxygen gas, they will have an electronegativity difference of 0. And this is obvious because both oxygen have the same electronegativity difference. If I keep by the former values I chose, I said, let's say the electronegativity difference, electronegativity of oxygen is 3. 3 minus 3 will give us what? 0. Since the electronegativity difference is 0, it means that they will not have a dipole moment. Because you can see this statement, we said dipole moment arises from differences in electronegativity. So it means both ionic bond and covalent bond can have dipole moment. But for dipole moment to be present in any bond, that bond must be formed by two different atoms. Once it is formed by identical atoms, it can no longer have dipole moments. So other examples of identical atoms with a covalent bond is your nitrogen gas, N2, hydrogen gas, oxygen gas, which is the example I've given, etc. All those compounds, all those molecules will not have a dipole moment because they do not have electronegativity and they do not have what we call separation of charges. They do not have separation of charges. I haven't mentioned that the third point here is that the larger the difference in electronegativity, the larger the dipole moment. Now you see that it means that the larger the difference in the electronegativity, the more the dipole moment. This automatically tells us something, that since ionic bond is formed between metals and non-metals, and then we know that metals are found on the far left of the periodic table and non-metals are found on the far right. It means when a compound is formed having ionic bond, the electronegativity difference will be large, since we said electronegativity difference increases across the period. So for instance, hydrogen will be having an electronegativity difference of maybe 1, or let me use sodium chloride. Sodium will have electronegativity of about 1. Then chlorine, which is on the far left of the non-metal group, is going to be having a higher electronegativity difference of about 3. So by the time I subtract it, I'll be getting an electronegativity difference of 2, meaning that the farther apart they are, the greater the dipole moment. So that is what this statement is telling us, that the larger the difference in electronegativity, the larger the dipole moment. The distance between the charge separation is also a deciding factor into the size of the dipole moment. So take note of this. The distance between the charge separation will also tell us, will be a deciding factor into the size of the dipole moment. And lastly, the dipole moment is a measure of polarity of molecule. This is a very important statement. Dipole moment is a measure of the polarity of molecule, meaning that when you hear the word dipole, what should come to your mind is di in science means 2. Di means 2, then pole means 2 poles. 2 poles. That means any molecule that has 2 poles. And what are these 2 poles? The positive and the negative poles. So a molecule that has 2 poles is said to be dipole. And whenever molecules have positive and negative charge, we said such a molecule is polar. Such a molecule is polar. So dipole moment is also the measure of polarity of the molecule. Okay, furthermore, let's see some more information about dipole moment. A bond dipole moment is a measure of the polarity of a chemical bond between 2 atoms in a molecule. Take note of the word bond dipole moment. Bond dipole moment. It means that there is difference between the molecular dipole moment and the bond dipole moment. The bond dipole moment is the measure of polarity of chemical bonds between 2 atoms in a molecule. You know, we have some molecules having 3, 4, 5 atoms. For instance, if I have CO2, which is carbon dioxide, in carbon dioxide, how many bonds, how many atoms do I have in carbon dioxide? Carbon dioxide, we have 3 atoms, that is carbon, oxygen, and then another oxygen. Carbon with a oxygen, and then with another oxygen. So they are bonded together with double bonds. If you remember your Lewis structure, you will know that they have double bonds between the 2 carbon atoms, and we might still look at that, how to get the molecular structure as we proceed with this course. So now this is the structure of carbon dioxide. Now in carbon dioxide, you can see we have a bond between oxygen and carbon, and then another bond between carbon and oxygen. So there are 2 different bonds. Each of these bonds, the whole molecule, we have what we call molecular dipole moment, while each of these bonds, we have what we call bond dipole moment. So there are going to be 2 bond dipole moments in carbon monoxide, but there will be only 1 molecular dipole moment. So take note of that. Also, it involves the concept of electric dipole moment, which is a measure of the separation of negative and positive charges. I think we've already explained that. The bond dipole moment is a vector quantity since it has both magnitude and direction. So when we talk about dipole moment, it is a vector quantity. That's why we represent it with an arrow. You see it in the next slide where I stated that. If I write such a structure like this, I will represent it with an arrow moving towards the negatively charged molecule, showing that the direction of dipole moments always move towards the negatively charged molecule. The oxygen here, we have a partially negative charge, while the carbon here, we have a partially positive charge. So that's what we are going to be having here. We are going to be having a partially negative charge and a partially positive charge. Then at the tail here, towards the positive charge, we represent it with a cross, showing it is positive. So the tail will be crossed, and then the arrow will face towards the negative charge. The same thing we will call in this. We are also going to have something like this, facing this direction, and then have a cross. So this is, you can see both dipole moments facing the negatively charged atom. So the bond dipole moment, I said, is a vector quantity. An illustration describes the dipole moment that arises in hydrogen chloride molecule below. You can see an illustration here. This is a dipole moment between hydrogen chloride. Hydrogen chloride is a ionic bond, so definitely they will have difference. The electronegativity difference will not be zero. So definitely they will have what we call dipole moment. And they have, the dipole moment they have is a bond dipole moment. But you see in hydrogen chloride, there's only one bond. So it means the bond dipole moment will also be equal to the molecular dipole moment. But in the case of CO2, the bond dipole moment will not be the same as the molecular dipole moment, because you can see the bond dipole moment, there are two different bond dipole moments. Then by the time we sum them, we are going to get the molecular dipole moment. So that is what we have here. So let's proceed. Okay. So I said we have the bond dipole moment and also we have the molecular dipole moment. Do not mix them together. Now, important points on dipole moment. The dipole moment of a single bond in a polyatomic molecule is known as the bond dipole moment. You can see I'm restating those points, those important facts for you to keep put in memory, which we have already stated earlier. I said the dipole moment of a single bond in a polyatomic molecule. Polyatomic molecule is a molecule containing more than two atoms. Example, SO3, CO2, H2SO4, etc. Once it has more than two atoms, we call it polyatomic molecule. And then I said the dipole moment between a single bond, like the one between the carbon and the oxygen I showed you in the previous slide, or between the oxygen and the carbon, those single bond dipole moments are called bond dipole moment. And it is different from the dipole moment of the molecule as a whole. Also, we already stated that dipole moment is a vector quantity, and the meaning of that is that it has magnitude and it also has definite direction. Being a vector quantity, it can also be zero, as the two oppositely acting dipole bonds can cancel each other out. If you still remember vector quantities, one of their properties that they can be zero because they can cancel each other out. If you see the last dark structure I drew was the structure of CO2, and I showed you that in CO2 we have the carbon. Look at this now. This is the oxygen bonded to a carbon, which is bonded to another oxygen. Now, I showed you the dipole moment. We move in this direction. This is the direction. Dipole moment has direction and magnitude. This will be the direction of the second dipole. Can you see they are moving exactly in opposite direction? The meaning of that is if the bond dipole moment here happen to be 2.5, just for an instance, it means the bond dipole moment here will also be 2.5. But what will be the difference? Since they have different direction, it means if one is positive, the other one will be what? Negative. So positive plus 2.5 minus 2.5 is equal to what? That's equal to 0. Very correct. That's equal to 0, meaning that in CO2 we have bond dipole moment, but we not have a molecular dipole moment because each of the dipole moments will cancel each other out. By convention, it is denoted by a small arrow with its tail on the negative center and its head on the positive center. In chemistry, the dipole moment is represented by a slight variation of arrow symbol. It is denoted by a cross on the positive center. So in chemistry, this is how we represent it. I said it is denoted by a cross symbol on the positive center. The carbon will be having the partially positive charge, while the oxygen will be having the partially negative charge. But you ask me that, well, why is carbon carrying a partially positive charge, even though we know that carbon is also a non-metal? Both carbon and oxygen are non-metals. In the case of hydrogen chloride that we saw in the previous slide, it was very much understandable that hydrogen is the one that will carry the partially positive, while chlorine will carry the partially negative. But in the case of carbon dioxide, both of them are what? Are non-metals. So how do we decide which one carries the partially negative charge? The one with the higher electronegativity will carry the partially negative charge. So how do I know oxygen has a higher electronegativity than carbon? I told you electronegativity increases across the period. It means as I'm going from left to right across the period, from the metals to the non-metals, electronegativity is increasing. And if you should remember your periodic table properly, you know that we have carbon, nitrogen, oxygen, meaning that carbon comes first before nitrogen and before oxygen when you are moving from left to right. So oxygen, we have a higher electronegativity. So therefore, it will be the one carrying the partially negative, whereas the carbon will be carrying the partially positive charge. And you can see I drew the arrow facing the negative charge, and then I used a cross tail to denote where the positive charge is. In case of polyatomic molecules, the dipole moment of the molecule is the vector sum of all present bond dipole moments. You see here now, I told you, after knowing that the bond dipole moment here is 2.5 and the one here is plus 2.5, how do I know the net dipole moment? That means the molecular dipole moment. All I need to do is to do a vector sum, that is 2 plus 2.5. You know, I said this will be minus 2.5. If this is plus 2.5 to be minus, if this is minus, this will be plus, because they are in opposite direction. You can see the arrows moving in opposite direction. So I'll do the vector sum, which is minus 2.5 plus 2.5, which will equal to what? 0. Is that okay? So in order to get the total dipole moment, I'll just sum up all, I'll do the vector sum of all the various bond dipole moments. I hope that is clear. So that's how to arrive at the bond dipole moment, at the molecular dipole moment from the bond dipole moment. But we shall see that very soon. Good. Now here you can see that we have, you can see a formula here, the mathematical representation of dipole moment. We represent it with this Greek letter. It's called mu. So dipole moment represented with mu is equals to charge, which we represent with Q, times distance of separation, which is R. So to calculate dipole moment is equals to charge times distance. Dipole moment equals charge times distance. And it is denoted in D by units, denoted by D. So whenever I want to measure dipole moment, we measure dipole moment in D by. Normally, if you multiply charge times distance of separation, the unit you will get is coulomb meters, because charge is in coulombs and distance is in meters. So by the time I multiply charge times coulomb times distance, I'm going to get coulomb meters. But in order for uniformity, we represent dipole moment using a symbol called dBi, which is the name of the scientist who discovered this concept. So what is the relationship between coulomb meters and dBi? 1 dBi is equal to 3.33564 times 10 to the minus 30 coulomb meter. You don't need to memorize this value. Whenever I give a question to solve, I will definitely provide these values for you. So I said C is coulombs, YM denotes meter. Now, for bond dipole moments, I said the bond dipole moment that arises in a chemical bond between two atoms of different electronegativity can be expressed as follows. So you can see the formula is just the same, just that we represent it with a little bit different value. Here I said the dipole moment for the whole molecule is charge times distance, where I represented my charge with Q. But in the case of the bond dipole moment, I said mu is equals to, this symbol is called sigma times distance. So instead of saying Q times R, which I used here, Q times R, I said sigma times D, but they still mean virtually the same thing. The sigma here signify partial charge. So it's also charge, but not full charge. So I represent that with partial charge times D is distance, in contrast with R used here for distance. So don't get it twisted. It is still the same thing. Mu is equals to Q times R. If you remember that, that's fine. You can still use that same formula to solve for the bond dipole moment. So it's just represented so that we can see the difference between them. Okay, now let's see an example. Dipole moment of beryllium difluoride. Now we can see beryllium difluoride. This is the structure of beryllium difluoride. Beryllium difluoride is a linear molecule. I will show you how to know the structure of a molecule, because it is very, very important for you to know the structure in order for you to be able to determine the dipole moment. If you don't know the structure, you cannot determine what the dipole moment of beryllium difluoride will be. But here I already provided the structure. You can see the structure is linear. That means it's a straight line. is a straight line. Now, having seen that it's a straight line, from here I can also say that the dipole moment of beryllium and fluorine here will be equal to the dipole moment of beryllium and fluorine here, but they will be of opposite charges. Do you agree with me? Yes, I believe you do. From what we said in the previous slide, I told you that each bond has its own bond dipole moment, and the molecular dipole moment is the what? Is the vector sum of each of the bond dipole moments. So let's take, for instance, that this has a bond dipole moment of 4. Let's say it has a dipole moment of 4 dBi. This will also have a dipole moment of what? Of 4 dBi. How do I know? Because they are the same. It is a dipole moment between the same atoms, beryllium and fluorine. The only difference is that they are moving in opposite direction. Don't forget, we said dipole moments have a magnitude and they also have direction. And you can see the way direction is being drawn. You could be asked to tell where the direction of the arrow will be facing in a particular bond dipole moment. You'll be expected to be able to show me that the arrow will be facing towards the negative charge, while the cross tail will be towards the negative charge. So since I said they are in opposite direction, it means if this one is plus 4 dBi, this will be minus 4 dBi. Do not get it, do not make a mistake. I'm just making up these values. I did not calculate them, just to illustrate this example. So in order to know the bond dipole, total dipole moment of beryllium, it will be the vector sum, meaning that I will say 40 dBi plus minus 4 dBi, which is 4 dBi minus 4 dBi. 4 dBi minus 4 dBi will give me 0. So it means that there will be no molecular dipole moment in beryllium difluoride, even though it will have bond dipole moment. This is a very important statement, because I could ask you, will beryllium difluoride have dipole moments? Will it have bond dipole moments? You will tell me whether it has or not. Obviously, it will have, because the molecules between the bonds, the atoms between the bonds are not identical. I told you, once there's an electronegativity difference between the atoms that make up that bond, then it will have a dipole moment. But only when they're identical, like we have in oxygen gas, O2, H2, N2, etc. That's only when it will not have a bond dipole moment. But despite the fact it has a bond dipole moment, that does not guarantee that it will have a molecular dipole moment, because we can see in beryllium difluoride now that even though it contains a bond dipole moment, beryllium difluoride lacks a molecular dipole moment. So because by the time you sum up the vector, you do the vector sum of the bond dipole moment, it will be equal to what? 0. So from the illustration above, I said it can be understood that two individual bond dipole moments cancel each other out in beryllium difluoride because they are equal in magnitude and are opposite in direction. Therefore, the net dipole moment of beryllium difluoride will be what? 0. All right. So let's proceed. Let's say another example, dipole moment in water. In the case of water, from the VSAP theory, VSAP here, which is valence shell electron pair repulsion theory, you have been taught that in your previous encounter with molecular structure in 200 level. But even if you can't remember that, I would still refresh your memory a little bit on how to know the molecular structure, whether using VSAP or VBT, valence bond theory. So, but according to VSAP, we know the shape of water is not going to be straight. Even though water has the same genetic makeup, let me use that word, as beryllium fluoride. What do I mean by that? Is I look at beryllium difluoride. Beryllium difluoride is BF2. BF2, meaning that I have 2 beryllium and I have 1 beryllium and I have 2 fluoride. In water, water is H2O, meaning that I can also write it in another form and say water is OH2. OH2. It is the same thing as H2O. I just put the oxygen in front. The purpose of doing this is so that you can see that both beryllium and water have a genetic structure of AX2. AX2 meaning that there's a central atom and 2 other atoms attached to the central atom. You can see both of them have this genetic makeup of AX2, meaning that we could guess and say water is also linear like beryllium difluoride because they have the same genetic makeup, which is AX2. But this is not so in reality. The reason is that in water, there is what we call lone pair of electron on oxygen. Actually, there are 2 lone pairs of electrons on this oxygen atom that is not being shown here. So here we have a lone pair, and then here we also have another lone pair in oxygen. This lone pair, instead of this bond to be straight, this lone pair repels the bond. It repels the bond. And that's what Visap told us. That's the second postulate of Visap theory, that lone pair bond pair repulsion is very large, meaning that the lone pair will repel this bond. There's also a pair of electrons on this bond, forming this bond between oxygen and hydrogen. So they will repel each other. And because of that, instead of water to be linear, the shape of water becomes bent. Now, what's the implication of this on dipole moment? If water peradventure happens to have a dipole moment between oxygen and hydrogen here to be 4 dBi, just using that as another example. On this other end, it will also have a bond dipole moment similar to the one on the other hand. Let's say 4 dBi also, for instance. But they will not have the same charge. They will not have opposite charge, sorry, because you can see that they are not linear. If they were linear, they would have had exactly the same, they will have had the opposite charges to each other. And so by the time you sum them up, they are going to give us what? 0. But in the case of this, they do not have such charges. They do not have opposite charges because they are not linear. So once it is not linear, it means water will have a bond dipole moment. The bond dipole moment of water will not be equal to 0. The bond dipole moment of water will not be equal to 0. But in beryllium difluoride, the bond dipole moment is equal to what? Is equal to 0. Sorry, not the bond dipole moment, the molecular dipole moment. Beryllium difluoride has 2 bond dipole moments, but its molecular dipole moment, which is the net dipole moment, will be equal to 0. In water, there are also bond dipole moments, but the net dipole moment of water will not be equal to 0. So if you are asked why, the simple explanation to that is, despite the fact that beryllium difluoride and water have the same molecular structure format, that means the same basic genetic format of AX2. Both of them have the same genetic structure of AX2. Water is not linear. Water is not linear because of the presence of lone pair. So because the shape of water is bent, the dipole moment will not cancel each other out. You can see that clearly explained in the slide above. So in water, they will not cancel each other out, unlike what we can see in beryllium difluoride. Okay, let us proceed. So let's see a little bit more on how to calculate on dipole moment. I said let's consider a simple system of a single electron and proton separated by a fixed distance. When proton and electron close together, when proton and electron are close together, the dipole moment, that is the degree of polarity, decreases. Obviously, since we said the distance will also determine the dipole moment, it means the farther apart they are, the larger the dipole moment. So if they are close, it will decrease the dipole moment. However, as proton and electron get farther apart, the dipole moment increases. So you can see this now. You can calculate the dipole moment for protons and electrons. You can see this value 1.60 times 10 to the minus 9 coulomb is the charge of an electron. You don't need to memorize that. The charge of an electron is 1.6 times 10 to the minus 19. That's where I got this value from. And then I said if they have a fixed distance apart, let's take that distance between them to be equal to 1 Armstrong. Is that okay? 1 Armstrong is the same thing as 1 times 10 raised to the power minus 10 meters. Don't forget that 1 Armstrong is the same thing as 1 times 10 raised to the power minus 10 meters. So this is the charge of an electron times 1 Armstrong distance, which we must change to meters. It will give us 1.60 times 10 to the power minus 29 coulomb meter. But don't forget, we are supposed to measure it in dBi. And I told you that 1 dBi is equal to 3.336 times 10 raised to the power minus 30 coulomb meters. Don't forget, I already stated that earlier. So in order for us to convert coulomb meters to d by, all I need to do is divide by that value, 3.336 times 10 raised to power minus 30. If I divide, I'll get 4.80 d by. This is a very important figure. We are going to use it to derive for other d bys, for other distances of protons and electrons. So we have 4.80. So using that 4.80 now, I said 4.80 d by is a key reference value and represents a pure charge of +1 and -1 separated by 100 picometer or 1 Armstrong. So 100 picometer is the same thing as 1 times 10 raised to power minus 10. 1 Armstrong is the same thing as 1 times 10 raised to power minus 10. So don't get it twisted. Pico means 10 raised to power minus 12. So by the time I put this 20, it becomes 10 raised to power minus 10. 1 times 10 raised to power minus 10. So if the charge separation were increased, then the dipole moment also increased linearly. So it means if I'm increasing the distance between the two charges, as in between the proton and the neutron, the dipole moment will also increase linearly. So we already know that 4.80 d by is for 1 Armstrong or 100 picometer. So if I tell you if the proton and electron were separated by 120 picometer, so I could give you in your quiz, I could ask you if proton and neutron are separated by 200 picometer. Now, I don't need you to solve 4.80 d by for me. I would already give you and tell you that the distance between proton and neutron separated by 100 picometer is 4.80 d by. What will be the distance? What will be the dipole moment if the distance is 200? So all you need to do is just tell me the dipole moment will be equals to, if I say 120 now, I just put that 120 divided by 100. Why am I dividing by 100? Is that this 120 picometer is the one I want to solve. So I have to divide it by the 100 picometer, which was used to calculate this 4.80. So that would be 120 divided by 100 times 4.80 d by, and that will give me 5.76 d by. If I do for 150, I'll say 150 divided by 100 times 4.80 d by, it gives me 7.2. 200 give me 9.60. You can see it is increasing as the distance increases. So that proves the fact that the larger the distance, the higher the dipole moments. Let's look at polarity and structure of molecules. This is very important. Now, the shape of a molecule and the polarity of its bond determine the overall polarity of that molecule. The shape of a molecule and the polarity of its bonds determine the overall polarity of that molecule. A molecule that contains polar bonds might not have an overall polarity depending upon its shape. You know, I already said that earlier. If the shape is symmetrical, for example, a symmetrical shape is linear, like we could see in beryllium difluoride. If they have a symmetrical shape, automatically, even though they have bond dipole moment, they will cancel each other out. So a molecule can only be polar if the structure of the molecule is not symmetric. You can see the statement symmetric. So you can see this is a linear molecule in CO2. They will cancel, the bond dipole moments will cancel each other out. So it will have no net dipole moment. But in water, because the molecule is bent, they will not cancel each other out. You can see the direction of my arrow here. This one, the direction, they are opposites, in opposite direction. This is going this way and this is going this way. But in water, you can see it is moving towards the oxygen. Why? Oxygen is more negative than hydrogen. Don't forget I told you electronegativity decreases across the period, meaning that it increases across the period from left to right. So it means oxygen will have a higher electronegativity than hydrogen. So the arrow must be facing oxygen, which will be carrying the negatively charged, partially negative charge, while hydrogen is carrying the partially positive charge. But in the case of CO2, carbon is less electronegative than oxygen. So oxygen will still be carrying the partially negative and the arrow will be facing the oxygen. Don't make a mistake here, because the common mistake you can make is to just draw the arrow in the same way you do it here and make the arrow face hydrogen. That would be very, very wrong. And in that case, you would be getting the dipole moment the next dipole moment will be 0 because the direction will be opposite. But since the direction are facing each other, it means instead of them canceling each other out, they will sum up together. So once they sum up, it will give us a bigger value. So the net dipole moment if this was to be 4d by 4d by, the net dipole moment would have been 8d by. But here, if this is 4d by 4d by, one will be minus 4, one will be plus 4, and they cancel each other out. So although a polar bond is a prerequisite for a molecule to have a dipole moment, not all molecules with polar bond exhibit dipole moment. Now, this part is going to help you answer a lot of questions on that dipole moment. You need to know all these shapes, and you need to know how to arrive at them. You need to know all these shapes and know how to arrive at them. So the first shape here is we have linear, we have trigonal planar, we have square planar, we have tetrahedral, we have trigonal bipyramidal, and we have octahedral. These 6 shapes are all symmetrical. They are symmetrical, meaning that there's a way I can divide them into 2 equal halves. And the implication of that is that they will cancel each other out. Once you have any molecule that has any of this shape, whether linear, trigonal planar, square planar, tetrahedral, trigonal bipyramidal, octahedral, then it means that kind of a molecule will have a 0 net dipole moment. There will not be a net dipole moment, although it will have bond dipole moment, but the net dipole moment will cancel each other out. For the purpose of quizzes, I wouldn't be expecting you to be finding out the shapes yourself. I would state it if I need you to know. I'll state it there that the shape is trigonal planar or the shape is octahedral, and then I'll ask you for the net dipole moment. But if it were to be your exam, I would not tell you the shape. You will need to find out the shape of that molecule yourself, and I'll show you how to arrive at the shape in another module of this course. Okay, so looking at this example, C2CL4. C2CL4 is our carbon, 2 carbons, and 4 chlorine. That's what makes up C2CL4. And the 2 carbons are the central atoms, so they combine together with a double bond, and then each of them carrying a chlorine atom. Each of them carrying a chlorine atom, making the C2H4. So although Cl, which is the carbon and chlorine bonds, are rather polar, the individual bond dipole moment cancel each other out in this symmetric structure. And then the total dipole moment, is the net dipole moment, is 0. Why? The structure you can see here, this structure here is what we call a trigonal planar. Trigonal planar, this is a trigonal planar. The structure here, each of these carbon has what we call a trigonal planar. This carbon has a trigonal planar. This carbon has a trigonal planar. So you ask me, how do I know that the structure of these carbons are trigonal planar? So we are going to look at that when we begin to discuss the shapes of the molecule, which I will discuss with you in the next module, where we will be discussing dipole moment further. So you will see how I can distinguish and tell that, okay, this shape is trigonal planar, this shape is tetrahedral, etc. So, but here, obviously, it is going to be a trigonal planar because of the double bond, which is a sp2 hybridization. So from here now, since I know it is trigonal planar, automatically I know it will be symmetrical. And you can see my arrow is facing the chlorine because the chlorine has a higher electronegativity than carbon, meaning that chlorine will be the partially negative and carbon will be the partially positive. You can see the arrows are not facing inside, they are facing outward. So this will cancel out this will cancel out this, and then the net dipole moment will be 0. So relationship between bond length, electronegativity, and dipole moment in simple diatomics. We'll see it here. In simple diatomic, you can see the bond length in Armstrong. Of course, Armstrong means 10 raised power minus 10 meters. For hydrogen fluoride, you can see the bond length is 0.92. You can see the bond length is 0.92 in hydrogen fluoride. When we move to hydrogen chloride, the bond length increases to 1.27. Hydrogen bromide, you can see the bond length also increases. Hydrogen iodide, the bond length also increases. So as you are going down the group, you can see the bond length is increasing. And as the bond length is increasing, what's happening to electronegativity difference? It is decreasing. As bond length increases, electronegativity difference is decreasing. You can see electronegativity difference of hydrogen fluoride is the highest. As the bond length is increasing. As the bond length is increasing, the dipole moment is decreasing. And then finally, what is happening to our the electronegativity difference? What's happening to the dipole moment? You can see dipole moment is the product of electronegativity difference here. Is as a result of your electronegativity difference. So the higher the electronegativity difference, the higher the dipole moment. You can see this 1.9 electronegativity difference. Dipole moment is 1.82. This one became 0.9 electronegativity difference. The dipole moment also reduces. As electronegativity difference is reducing, dipole moment is reducing. So take note, bond length, as the bond length is increasing, electronegativity difference, as the bond length is decreasing, as bond length is increasing, the electronegativity difference is what? Is increasing. And dipole moment is also increasing with increasing electronegativity difference. So we shall stop here today. And in our next module, we will discuss some examples, and then we move on immediately to magnetic dipole moment. So until then, I would enjoy you to try your answer on as many questions as possible. Put up structures yourself and task yourself on knowing whether the dipole moment would be 0 or not, or whether the dipole moment would be greater than 0. So thank you so much for listening. See you next class.